Good morning. Hi, everybody. How's it going? Good. So in today's lecture, in the lectures for this, in the lectures of this week in the lab, we're going to be talking about something really interesting. And yeah, so we're actually going to be talking about this, and surprisingly enough, this. So this one and that one. And it might sound weird to you, but that's actually true. So we're going to talk about a concept called recursion in this lecture and in the next lecture. For today, we'll be working on recursive coding and programming and algorithms. And in the next lecture, we're going to be talking about recursive data structures. But now let's first understand what recursion means. Okay, let me show you this image in a higher quality over here. Okay, so if I want to describe the structure of this plant, I would say that there's a stem and a number of branches, and on each branch there's a lot of leaves that we can see. And okay, so that's the overall structure. Now if I focus on, for example, this little guy over here and start to describe that, we again see that there's a stem, and then again there are branches and branches. And if you zoom further in and you want to describe one of these things over here, again there's a kind of a stem in the middle, and then again there are branches. So you can see that there's a kind of a similar structure. As you zoom in, the way that the structure is defined and described does not change, right? So the overall structure of this whole plant is similar to the structure of each one of these branches, and each one of little branches is also can be described similarly to the larger branch, to the outer branch. So we have an outermost structure, and then there are levels upon levels of the same structure. This is one depiction of the idea of recursion. So recursion means a process or a structure that can be defined in terms of itself. Okay? So here, whatever goes on in the outermost structure can also be applied to the inner structures as well. So what is that, that stem over here? That's actually, except for the scale, it's quite similar to the outermost structure. And as we zoom in, again, this little thing over here, again, is very similar to the larger structure that contains it, and so on and so on. So in this case, it doesn't go like into infinite levels of depth, but this is kind of the idea, something that can be described in terms of itself. Okay. Now, in programming, this is an idea that's very interesting to us, because there are a lot of situations when we want to write the code for an algorithm that we apply exactly the same thing over and over again to our problem. And that can be formulated in the form of a recursive code. And this is what we're going to be learning in today's lecture. Okay. So as you can see here, this plant over here, it does not go into infinitely more deeper levels. It stops somewhere. However, at least in mathematics, we have structures that do not become simpler as we zoom in further and further. I don't know if you've heard the word fractal. Yeah, so fractals are an example of such structures. For example, one of the most famous ones is this, what's it called? The Mandelbrot fractal. So this weird thing that you see on the screen, it actually repeats itself recursively, infinitely. And there's actually a nice animation that shows this. So let me show you this. If I can zoom in. Okay, so you can see that as we zoom in, we will find the same structure over and over again. Okay, yeah. So this is kind of the idea. And this actually challenges the whole idea of analyzing things. So for example, in physics or in other fields of science, when we zoom in, we expect things to become simpler eventually so that we are able to analyze them. But at least in the world of mathematics, there are some models that no matter how much you zoom in, that phenomenon does not become simpler. That's a very interesting idea. As a kid, I used to think, what if our entire universe is actually inside of an atom of another universe, which is also inside of an atom of another universe, and so on and so forth. But I mean, we don't know if that's true. It would be so cool if that's true. But this is just kind of an introduction into what the idea of recursion is. Okay, let's get started with the lecture material now. All right. So let me. Yes, all right. Okay, and I've made some modifications to the lecture notes, and I will push an update to the course repo at the end of this lecture. So don't worry if your version slightly differs from mine. All right. So here I have a piece of code. You don't need to understand what the code does, but it basically just represents this idea of recursion in the form of some tree graphics that we can make. So you can disregard this thing over here, actually. Let me just minimize this and go back up. Okay, run this code, and let's run this function. What it does, it creates a tree graph for you. And the way that it works is that we have a number of limited shapes in this function. Let me show what are the options. So we have a square, hexagon, star, and V. Whenever the code sees a V, it just branches off. And whenever it sees a shape, one of these shapes, square, hexagon, or star, it just stops there. Okay? So there are two V's in here because I wanted to increase the probability of that branching happening. Okay. Let me go back up, run this code a couple of times. You can see that here the code stopped here because there are two, one hexagon, one square. Let me run this again. Okay, bunch of squares, but you can see the branching. All right, run it again. Let's see if we can get, yeah, so that's something interesting. And also this one. So where is recursion in this case? Recursion in this case is that any sub-branch of this entire tree can be actually its own, a tree by its own, right? So this part over here, this can be considered a tree. This larger thing over here with 3 branches can also be its own tree. This also can be its own tree. Here again, the same thing. And you can see that this pattern repeats itself over and over again until it stops with a condition. Okay, yeah, this one is also quite nice. So as soon as we hit a shape, a particular shape, we stop. And if we hit a V, we branch off. Okay, so again, each one of these subtrees are in their own right a tree by themselves. Okay, so this is just, again, a depiction of the idea of recursion. Any question about this graphic over here? Again, the idea is just that there are substructures which are exactly similar to the outer structure or to the larger structures. Okay. All right. So here, in order to introduce you to the idea of recursion inside of code, I'm going to take a very step-by-step approach because it tends to be a little tricky when you first learn about recursion and the way that you can implement it inside of code. So let's get started with a few cases. I have 3 cases here. Little by little, we build up the skills to be able to code a recursive function. Okay, so here I have a function h, the simplest function, Python function that you can imagine. It doesn't take any input. It returns 0, always. Okay, we can call that. Oh, return 0, nothing interesting happening here. Okay, now we have a function called g, which inside of it, it calls h and adds 1 to that. Okay, and now let's call g. All right, so what happened here is that this function called h, and it got 0 back, and added 1 to that, and then returned that whole thing to us, which is 1. Okay, let's move on. Now let's define another function called f, which calls g and adds 1 to that and then returns the results to us. Okay? And when we call f, it returns 2 because now there are 3 levels that it goes into. So g calls h, and then f calls g, and then the results are returned back to us. Okay, now let's consider this case over here, function that has inputs but no outputs. And I have added a couple of print statements here to see what's going on. When the function is called, we will see these print statements being shown on the screen, and we will know what's going on in that case. So diff h in, and let's run that, h of 3. Okay, you called h with argument 3, obviously. Okay, and then ending h with argument 3. Let's run the same thing with h of 2. Okay, this is working as expected. So it just reads the argument and shows us what that value was. Okay, now let's define a function g of n, which does the same thing, kind of the same thing. It prints a statement over, prints something over here that actually shows us the argument, similar to h, but in the middle, in between those two printing statements, it also calls h, but h of n minus 1. Let's see what happens here. Okay, g of 1. It says you called g, yes, this is that line, and then it says you called h with argument 0 because n was 1, and then inside of g we subtracted 1 from that original argument, and then we passed 0 to h. And then this goes inside of h, runs h, as we can see here. You called h with argument 0, ending h with argument 0. And then once it finishes running this function, it takes the result back to us into the main function g. Okay, it says ending h with argument 0, and now is the time that g can end its execution. Okay, now it says g with ending g with argument 1. So the idea of calling a function within another function. And one thing that you can see here is that whenever we see some function inside of a Python code, the main program stops, we step into the function, and then we run the function, and then once the function terminates, we come back to the main program, okay, with the return values. And whatever happens inside of the function just becomes destroyed by the main Python runtime. So here, this is the same idea. When we call g, okay, the main program stops, we go into g, and then inside of g, the execution of g stops because it hits this h function, so it goes inside of h. And now, until the running of h finishes, we cannot continue running g. So we step into h, we get back a value, and then we use that value inside of g, we return a value, and then we go back inside the main program. G of 2, okay, started with 2, h called 1, and then h ended with 1 because we're doing nothing with it, and then g ended with 2, okay? And same goes here for g of 3. Okay, so it's just the value of the argument that changes. Okay, now let's have another function called f, which does this exactly the same thing as g, but instead of calling h, it calls g. So we're creating another level on top of the previous level. So f calls g, g calls h, h runs, returns the value back to g, g returns to f, and then f returns to the main program. Okay, let's see. F of 5. All right. F was called with 5. G was called with 4 because n is 1 is subtracted from n. Okay, 5 becomes 4, 4 becomes 3. F calls g, g calls h, and then that's the innermost level. So h ends it's terminated, and then we have no return value, obviously, but it has to terminate in order to go back to g. So h is terminated here, g is terminated here, and then f finishes its execution. All right, and same goes here with a different argument. Okay, are there any questions about this sequence of things that we're doing? The way the function calling works inside of another function? Okay, let's move on. All right. So now I have a more complicated function that not only accepts some input arguments, but also returns something. So h takes in argument the parameter n, and then we return some value from that function. That's the only difference here. We're not doing anything with this n. We're just accepting that as a parameter, and then we just return a value that's defined inside of h. Okay, h of 5, starting h with 5, and then returning this value 0. Okay, now, g of n, pretty similar to h. Let me scroll back up, show you h. So h takes n, sets this value to 0, and returns value. This is pretty similar. Takes an n, and instead of setting value to 0, it reads something from h, and then adds 1 to it, and then returns that value. Okay. So 2 levels here. G is called with 10. H is called with 9, because this is what happens here. And then h here is going to be executed. What it returns is 0. So it gives that back to g, and g replaces this with 0, adds 1 to that, and then returns that value to us, 1. So this is expected to happen. All right. Now we add another level on top of that, similar to what we have done previously. So f calls g, g calls h, and the same sequence of things happens again. So let's see. F is called with this argument 11, g is called with this argument 10, h is called with 9, and h is the innermost level, and that's where we return something from h, so that's terminated, and 0 is handed back to g, and 1 from g is handed back to f, and now f can go on and compute this value over here. Finally, it returns the value to the main program. Okay. And because h starts with 0, we get this value 2 because there are 3 levels, 0, 1, 2. Okay. Now take a look at this sequence of functions. Okay. So I have just gathered everything in one place and removed some of the extra printing statements. Let's run that. Same thing should happen here. F of 11. Note that it doesn't matter what value of n I use here. The value that's returned from it depends on h and how many levels there are. Okay, because h here always returns 0. This value is handed back here. And again, this entire thing is going to be returned to f here, and then we're going to return something from that. This is starting to feel a little bit boring, but we have to build up the knowledge for recursion like this. Otherwise, it would be too confusing if we start with everything in one go. Okay, now let's run this F1000. Again, you know that this return value doesn't change because nothing is, we don't do anything with n. Okay, getting closer to what we want to learn here. All right, so take a look at these functions. Okay, so whenever f receives the value of n equals 0, it just returns something. Otherwise, it calls g. Whenever g sees 0, it returns 0. Otherwise, it calls h. Whenever h sees 0, it returns 0. Otherwise, it calls I. In this case, I doesn't exist. But let's see what happens if you run f, this sequence of nested functions. We run f for 1, and 1 is not equal to 0, so it calls g. Okay? And it calls g with 0. G sees 0, so it returns 0. Okay? And this value over here becomes 0, and then this returns 1 to us. Okay, this is why we see this value of 1. Now let's run g with 1. Okay, starting with 1, and then decrementing the value to 0, and then we get this return value of 1. So it does exactly the same thing as f. nothing is different, okay? So calling f is exactly the same as calling g, is exactly the same as calling h in case I existed. Okay. However, if we start running the code for larger values, we have to eventually hit this value of 3, okay? 0 works, 1 works, 2 also works, but here it says that this function name I does not exist. And that's to be expected, right? I doesn't exist here. So what if I want to apply something like this function f or g or h like 1,000 times or 1,000,000 times? Should I just write down all these functions, 1,000,000 functions, one after the other, so that I can run that particular program that does something exactly the same to the input that it receives from the previous level? Obviously not, because it's not practical. So here comes the main idea. So instead of doing all that, because f, g, and h, and I, and any other function that comes after that is exactly the same, why not just calling f itself? Because the structure itself does not change. So here we're defining f. Okay, if n equals 0, then return 0. Otherwise, call f again, because it's exactly the same thing. We're doing exactly the same thing with the input, right? Okay. Now, if I run this function, no matter what value I give to f, it will always run, right? F4. Again, it runs. So there's no limit to how many functions calls I make or what argument I use here for n. This function will always run. And I don't need to define 1,000,000 functions to do 1,000,000 operations of the same kind. So again, here, right now, you can see the idea of recursion here, something that's defined in terms of itself. Here, f is defined in terms of itself. Whatever it does is defined in terms of what it does. If you look up something that's funny that I found last night actually was that if you look for the definition of recursion in Google, it tells you that recursion is a process that is done in a recursive way. That's pretty recursive to me. Okay, what's recursive? A process that involves recursion. What's recursion? It's a process that involves... Okay, so the definition itself is recursive. Yeah, okay. So here again, you can see f here, and inside of its own definition, you can see f again. Pretty much similar to the plant that we saw. We saw a big plant, there were branches. Those branches all looked exactly in the same way as the bigger plant did. Right? And all the smaller structures, again, had the same kind of thing going on for them as the outer levels. That's recursion. Okay. One very important thing that I will come back to is the idea that, that each function inside of Python or, in any programming language is that each function lives inside of its own little universe. So whatever happens inside of one function is not visible to the main program or to the function that called it. Okay, we return values from those functions or we take in inputs, but that's all we have. So that is the only way that this function can communicate with the outside world, the input arguments and the return value. It lives inside of its own universe. So, for example, what happens here if I call f is that n becomes equal to 1, and that is passed to f. And then inside of f, I also run f of n equals n minus 1. And in Python, in conventional code, in regular code, you cannot see something like this happening because two variables with the same name cannot be in the same place. But this is possible inside of a function of another function because each function has its own set of variables. Or in other words, it has its own scope. Okay? So this n, Python knows that this particular n belongs to that first level of f, and this particular n equals n minus 1, whatever that is, for example 2, this becomes to the second level. This belongs to the second level of that function. these are two separate things going on. Okay, so I will come back to this idea later. All right. Now, just in order to see what goes on when we run this recursive function, I've added these print statements over here to see it's kind of the sequence of things happening. So these are the only things that I have added. Nothing else is new here. Okay, f of 2. Let's see what happens. Starting f with argument 2. Okay, f is calling itself here, and it decrements that value by 1. Okay, it starts with 2, and then it decrements by 1, it becomes 1. Okay, it says starting f with 2, then starting f with 1, then starting f with 0. So every time f comes back here inside of its own definition and tries to run this, and note that we don't return anything yet. Okay, f goes inside itself, and then finally in the innermost level it hits 0. Once it hits 0, it returns this thing. It executes that block of code. Okay, n is equals to 0, so the innermost level returns 0, all right, ending f with n equals 0 and returning. Okay, and then now that is handed back to the upper level, and then that is also handed back to the upper level, and it's only then that we finally return something from the outermost level of f. Okay. Let me keep that on the screen just for a few moments. So, any questions about this particular piece of code? Does it make sense, the way that it runs? Yes. Okay, why it goes back to 1 and 2. Do you mean here, these last 3 lines? Okay, so when the innermost level finishes running, it hits this case, right? Okay, so the innermost level returns 0 here, and then that 0 is handed back to this value over here that was... Yes, f was called, and each call is waiting for the next call, and each call is then waiting for the other call. And unless we hit the end of all of that call sequence, nothing becomes executed in the middle. We have to hit that case, and then as soon as that returns, we go back up one by one. Okay? And it's only then that this particular line of code is executed. Okay, any other questions? Okay, so an important takeaway point here is that, again, when we call a function, we have to wait for it to terminate, and it's only then that we can continue executing the rest of our program. And here, when we go multiple levels deep, we have to wait for the last level to return something to us, and then we hand back that result over and over again to all of the other functions in that sequence, and everything can become executed and terminated in the end. Okay. Note that this thing that I have over here, if n equals 0, is called a base case. So if we didn't have this in there, what would happen in that case if I just remove that line? Exactly. So the code never stops because f just infinitely calls itself, and yeah, we get stuck. And it's similar to a situation that we've already seen. An infinite something. An infinite for loop, yeah. So if you have a for loop, or let's say a while loop, is more understandable. And if you don't have a stopping condition, it just loops forever. Okay, so this base case is something that we wish to progress towards, so that there is some point in the program that the program stops. Okay. All Stack Overflow. So now I'm going to tell you what is why this particular website is called Stack Overflow. Okay, so what we see here in this case, you can see F starting with 5, and then again F starting with 4, and F starting with 3. Okay, so in the main Python interpreter, there should be a way to keep track of all those function calls. Okay, so when F is called for, let's say, F is called with 5, okay, Python interpreter creates a data structure called a stack, okay? And it's a stack because if we put something on top of each other, we can only reach the item at the bottom if we pop all of the items at the top one by one. This is a particular data structure, very simple. It follows this idea of last in, first out. So you put things in, and then when you start to take things off this stack, you have to start from the top. So the last thing that got in becomes removed the first. So F is called with 5, then this particular thing, this F itself, calls F of 4, then F of 3, and finally F of 0. Okay, this is called a call stack, and each of these functions again lives in its own universe, and these are called frames. Actually, if you saw that somewhere, this is what it means. So each one of these is called a call frame, meaning that there's a scope for each function, and it has its own variables and things going on. Okay, when we start piling things up in this call stack, then whenever one of these functions returns something, okay, return 0 for example, then the execution of this one is terminated, and we just pop that off. Okay, and then this value goes into this particular call frame, and because it also returns something, we pop that one off as well. And then finally, we get back to F5, and we pop that one off as well, and the return value goes back to the main program. So this is a call stack, and this is the way that Python or any programming language keeps track of what's happening inside of multiple calls inside of a function. Okay, now, I told you that the execution of a function does not become terminated until everything else inside of that function is finished doing what it does, right? So if I have some data in here, then Python has to keep track of that data, has to store that data somewhere, and it actually stores it here in the call stack, okay? So this one lives in its own universe. We have to save all of the results for this universe, and then save everything here in this particular universe, save everything here in this particular universe as well. We have to keep track of things. Otherwise, when we start returning, we don't know what to do. Does that make sense? We have to save the intermediate results. Okay? Now, there's a risk here. If our call stack becomes too large, and we don't have a good strategy of managing that, then this stack basically overflows because there's not infinite space inside of the memory in order to keep track of like an infinite amount of things, right? And that's what's called a stack overflow error. So and this is why the logo is something like that. So you see a stack of items on top of each other, and then eventually it overflows and gives you that error. And usually programming languages have a strategy of telling you that there is something going on, you have to be careful. For example, Python does. Otherwise, your program just crashes because you run out of memory space, and then it just crashes. Okay. So let me show you what happens if we don't have a base case. If we don't have a base case, there will be an infinite number of calls to the same function, so stack overflow will happen. Okay, so here I have a function called infinite recursion. Here it just calls itself with I, where we just add 1 to I at every iteration. So you can imagine that this particular function call actually never stops. Let's run that, and let's start with 1, inf recursion of 1, then it goes and runs inf recursion of 2, inf recursion of 3, 4, 5, and it goes on forever. Let's run this. Okay, yeah, it goes all the way to 2969, And then finally, it gives you this error, recursion error, maximum recursion depth exceeded. And this is a way that, this is a strategy of Python that basically guards against crashing the entire Python interpreter. Instead of letting you run out of memory, it just tells you that we have exceeded the default depth that we have. And by the way, there is a way to change this limit of 2000 something, but inside of Python, if you're doing a recursion for more than 3000 iterations, it's probably not a good idea to do that with recursion. You have to do something else, like a for loop. Okay? All right. There is one other point that I would like to mention, but I will do that after the break. So let's take a break of 4 or 5 minutes, and then we'll be back. All right. All right, we're back. So, let me tell you that whatever we can do with recursion, we can also do with a for loop. Okay, that's always true. But why do we use recursion? What is this all about? Why should we go through all that trouble of understanding what goes on of multiple function calls and everything? Why is that the case? Why recursion is important? It's mainly because in a lot of cases, recursion actually leads to very clean code. So you can express a problem in a few lines of code by implementing it in the form of a recursion, instead of keeping track of things yourself inside of a for loop and writing multiple lines to execute whatever you need to execute. You can do it in much fewer lines of code and in a very elegant way. And it's very, very readable if you do it in that way. And the other reason is that, again, not the other reason, kind of the same reason. When we have recursive data structures, like a tree that we will learn about later in tomorrow's lecture, traversing the tree and checking out items inside of the tree is much, much simpler to do inside of a code that uses recursion. Okay. Now you might say, but how about this maximum depth of recursion or something like Stack Overflow? Doesn't that impede the whole process of writing things with recursion? Yes, that's true. In the most general case, you shouldn't use recursion for cases where you have a large number of calls to the same function over and over again. If you have, for example, a tree with a depth of, let's say, at most 100, then it's a good idea to use recursion. But if you know that you're going to be have a million levels to your tree, then recursion is not a good idea in that case. However, there's an important exception here. There are languages that are optimized for the idea of recursion and function calls. So mostly functional languages like Haskell and Scala. I don't have any experience in those languages, but I know that they're optimized for doing functional programming, meaning that your own tool is just calling functions. You don't even write for loops. You just use function calls in a recursive manner most of the time. Okay, Python does not really support a lot with recursion. One thing that could happen is that some languages, when they see a recursive code, if possible, they don't store the intermediate results, okay? And in that case, you actually won't ever see this Stack Overflow kind of thing. It runs just like a regular for loop. And you have to write your code in a particular way, and I will discuss this in the lab, maybe just to show you a glimpse, not that it's important. And this is called something, this is called tail recursion. Some languages optimize for tail recursion, and if the last thing that you do inside of a recursive function is just the call itself, you don't do any other computation, you don't store any more data, then the programming language actually doesn't create a call stack, and it just pops things off as you go through the execution. In Python, that's not possible. You'll eventually run out of memory space, so it's a good idea to limit recursion to cases where you can have an elegant solution, but you're not expecting to do something like for a million times. Okay, let's move on. Any questions about this whole thing of Python keeping track of things? Yes? Oh yeah, you can. Yeah, exactly. Yeah, eventually if you take a very large number and set it equal to the maximum recursion depth, then you'll eventually run out of memory. Not shut down, but the Python itself, the Python interpreter, it just crashes. Yeah, yeah. Yes. Can you repeat the question? Right. Oh, okay. We'll get to when we have multiple recursive calls in a function. I will discuss that in there. Okay, yeah, a good point. That's a whole different thing. Okay, now let's see maybe just one or two algorithms that we have seen in the previous lectures. So binary search. What we did in binary search was that we had an array of data that had a very important feature. What was that feature? With binary search, we wanted to search for a value. It was sorted, right? And because it was sorted, we could just split the data in half, look at the middle value, and compare the key to that value. If it was larger, we could just discard half of the data, and then discard half of the rest of the data, discard half of the data. And then this results in what is the big O complexity? Log n, because it takes log n steps in order to reduce the size of the data set to 1. So this particular algorithm lends itself to very nicely to like a recursive way of writing code, because whatever we do in each step is exactly similar to what we do in the previous step, right? You have a data, split it in half. You take this half, split it in half. You take that half, split it in half. So everything is just the same, right? Same idea, apply that over and over again until you reach that particular element if you want. Okay, so if you want to implement that recursively, this would be the code. We have a base case here. We say that when the length of the data is 1, meaning that there's only one item remaining, okay, then return data equals key, meaning that this will be either true or false. If that's the data that you're looking for, it'll be true. If not, then that particular data point does not exist in the list, and then you just return false. That's the base case, eventually. However, for any intermediate steps, you compute the middle index, right? And then you say, if key smaller than that value in the middle, then do binary search for half of the data. And if this is not true, then do binary search for the other half. And you can see that how nice the code looks. You say, okay, I have binary search data key, and I'm applying binary search data key again and again on the data that I have in a recursive fashion. Okay, and whenever this operation over here, this splitting, results in a list that contains only one data point, this line will be executed, and then we return either true or false. Questions about this code? So this one creates a call stack, first with the half of the data, then with a quarter of the data, then again and again, and until it reaches just one element at the top. And then it compares that element to the key, and then pops things off sequentially until we get to the bottom of the call stack. Yes? Oh, you mean returning the value itself rather than true or false? Mm-hmm. Okay, yeah, so that's the case here, right? The base case actually, oh, we don't do that here, right? You're right. Yeah, we don't, okay, yeah, you're right. We can write it in a better way. This is just to not basically clutter the code up with other things. You're right. Yeah, we have to check for the middle element because we might actually land on the correct value right in the first iteration. That's right. Yeah. Okay, just to see that this actually works, I have a bunch of assert statements, and this shouldn't return any error. You can check the data set out yourself. Okay. All right. Now we're done with this part. Let's now consider what's called multiple recursive call related to your question before. So, suppose that we have a function, a recursive function like this. It says it has a base case over here. It says if n equals 1 or 2, just return 1. Otherwise, return this thing. So f of n minus 1 plus f of n minus 2. Okay. And this is, if you remember, this is a particular sequence, has a particular name. Do you remember what that is? It's what's known as a Fibonacci sequence. Yes, yes. So this sequence has two recursive calls inside of it. And what should really capture your attention here is that we've discussed this idea that whenever we call a function, we have to wait for it to return something, and then we can continue executing the main function itself. And here it means that unless this function returns something to us, we cannot go ahead and compute this one. Okay, so just keep that in your mind. And let's just run this function, see what happens. Okay, f of 3 starts f with 3. And then, as soon as we start f with 3, it goes inside of this function over here and calls itself with 2, because n minus 1 with 2. Then inside of that, it again hits f n minus 1, so f with argument 1, so 3, 2, 1, and eventually it hits this base case, okay? And with that base case, it returns 1. Oh, sorry, yeah, okay, okay. Yeah, that's right. Okay, so these are just example values, not... Oh, yeah, I don't have the print statements here. Yeah, this is where it happens. Okay, let's see. Yeah, pretty similar. So, 4 initiates this f of 3 initiates f of 2 initiates f of 1, and then as soon as we hit the base case, then that returns 1. Okay, now that call returned 1, we can go back to the innermost level, and we have 1 here. And it's only then that we can call something else. We can continue with the execution of the right half. And I will show you a visualization of how this actually looks. This can be confusing if I tell you how this works over here. But let's move on. I'll show you what happens here. Okay. So f of 4 is called, and f of 4 calls f of 3. Okay. F of 3 calls f of 2. Okay. And then f of 2 triggers the base case. Okay. Now that this function terminates, we can go back to f of 3, right? Because this is terminated. In f of 3 itself, we have another term, f n minus 2. And because 3, here we have 3, and this is n minus 2, f of 1 will be called here, right? Because it's only then that I can move on to the next parts of the execution. Right? Yes? Do you have a question? Oh, okay. All right. So here, again, this is terminated, returns a value to f of 3. Okay, f of 3 executes the right-hand side, and that's f of 1. Again, it hits the base case. Okay. And then now we have both of the pieces. We pass them back to f of 3. Now f of 3 can return a value, right? Just 1 added to 1, and then that returns 2. Now we return 2 to f of 4. It's only then that f of 4 can go on and execute that right-hand side of itself. Okay, now we pass f of 2 to f of n minus 2, and then this one, because it hits the base case, it returns something, and eventually everything has terminated, and now we can compute the value of f of 4, eventually. Okay. Questions about this particular sequence of executing these functions? Let me keep that on the screen for a moment, for a few moments. No. That's actually the problem. If you happen to, this actually happens exactly in this case of computing the Fibonacci sequence. So you have to recompute a lot of stuff that you have already computed. So implementing Fibonacci sequence in a recursive way is not actually an efficient way of doing this. And let me tell you that, okay, let's discuss the time complexity. So what is the time complexity of this particular sequence? We have two 2 calls to the same function at each level. Sorry, for each function call, we have 2 other function calls, not at each level. So the time complexity will be in this case, it will be the number of function calls, because each function call is just constant in time, right? It just executes a simple statement. So if we count the number of nodes in that tree, that will give us the total number of function calls, and that will be the time complexity, right? Okay, so what do you think the time complexity is in this case? So the total number of nodes, right? Total number of function calls. What is the total number of nodes? Suppose that you start from this top node over here. By the way, this is the course's logo. Okay, so we have 2 nodes over here, and if we do something like 2 function calls for each, so this is f, but inside of f, we call f of n minus 1 and f of minus 2, right? So 2 function calls, these are the 2 function calls, and then here and here, here and here, and then again, okay, here, 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 and do this. Okay. Exactly. Yeah, we don't care about the cost. So, yeah, exactly. So it's the point is it's exponential, right? But let's see why it's exponential. We want to count the total number of these, okay? So here we have 1 node, right? In this level we have 2 nodes. In this level we have 4 nodes. In this level we have 8 nodes, right? And this is just 2 to the power of 0, 2 to 1, 2 to 2, 2 to 3. And this is a geometric sequence, right? And if you want to compute the sum of a geometric sequence, it has a formula that you can look up. And for example, if we go all the way up to, let's say 2 to k, this is 1 minus r, n plus 1 minus r. Okay. In this case, the factor, the constant factor here, if you divide this by this, or this by this, or this by this, the factor turns out to be 2, which in this case, this is the factor that we have here. So this is 2. This is 2. Okay. And this just results in 2 to n plus 1, and then minus 1. And in this case, this n is just 3, and 3 plus 1 will be 2 to 4 minus 1, and that is 15, right? And that is 3, 7, 8, and that's 15, right? So the important point here is that this is O of 2 to the power of n, because we don't care about the constant here, and we don't care about this constant here. So it's exponential, okay? Yes? Exactly. So if the function calls itself 2 times, we have 2 divisions. If it calls itself 3 times, we have 3 divisions. And it's the only thing that changes is this base here. So 3 to the power of n or 5 to the power of n, depending on the number of recursive calls that you make. Okay? So this is the time complexity. But interesting question here. What's the space complexity? I heard n. Yes, and why is that? Exactly, because of the concept of call stack, we can't execute anything until everything on one side finishes. So when we go into F, we first have to take care of this. In order to take care of this, we have to take care of this. In order to take care of this, we have to take care of this. And how many levels are there? N levels. So this will be O of n in terms of space complexity, because that's how many elements you build up on top of each other in the memory in order to compute something. Okay, so you want to compute this, you go all the way down, and then it's only then that you can compute that, and then now you go this way up. Okay, So in every computation sequence, you only consider n kind of spaces in the memory. You only use n spaces in memory. Yes, it's gone. It's gone. As soon as a function returns something, the function is destroyed. Yeah, yeah, it's destroyed. Yes, yes, definitely. Yeah. So if you store everything, the space complexity will also be to the power of n because that's how many. Yeah, yeah, exactly. And if you're mentioning that for the purpose of like efficiency, because we are doing a lot of computations that we eventually do on the other side as well, this is an idea that comes up in lecture 8, that we save something in the middle, cache the results in order for to use them later for efficiency. And that's coming up later. Okay. All right. Now, any questions about this whole thing over here? Yes. Only once, so that'll be constant, right? Right. It doesn't depend on n, then, right? So constant, yeah. Okay. All right. So this is what I mentioned here: O of 2 to the power of n. That's binary search. All right. Okay, this is an interesting question. All right, so here we have two recursive calls in the binary search algorithm. Is this O2 of n to the n? Exactly. Because there's an if-else statement, we actually don't do two recursive calls. We just compute one of those. We either execute this line or this line, not both. So this is, again, would be O of log n because we have log n steps in the middle. Okay. Now, let me see if we have other questions. Oh, we don't have any other questions. Okay. Since we have a little bit of time, let's, so if you have any questions about this, let's discuss them now. Okay. No, 1 is 3. Yes, definitely, because 3 to the power of n grows faster than 2 to the power of n. And those are but we call all of them exponential growth because algorithms like this actually have no practical importance because we can't ever use them for anything practical, basically. So we call all of them exponential. Yes. If you implement this in a nested for loop, then your for loop has to loop, for example, in this case, 2 to the power of n times. So it doesn't matter how you achieve that. You still have to make 2 to the power of n calls. Right. Yeah. Okay, any other questions? I just want to work on maybe a couple of activity questions since we have time. Okay, let's move on to that. All right. Let me see. Solutions. You're looking for that folder, I know. Okay. Okay, let's see here. All right. Consider this code over here. So just take a look at it for a few moments. And we just want to know what will be the result of running f for different values of n. Okay. There are a bunch of recursive calls in there. Okay. So let me this. So let's start with 0. If I run f of 0, we basically hit the base case, right? And what the function returns is just this empty space over here. So I'm going to do this. Okay. For 1, what do we do when we have f of 1? The else statement, right? Because 3 to 4, those are not 1. So we run this. Then this will be f of 0, which we already know the value for, plus e. So that's an empty space, and that'll be so because that's not a blank white space. That's just an empty string. Okay. Now f of 2. Again, we don't have n equals 2 in any of the base cases, so we have to refer to the recursive call here. Okay. F of 2 minus 1 will be f of 1 plus e. This is f of 1 plus e. That'll be e. Okay. Now f of 3. 3 is one of the base cases. So that'll be a, and then f of 2, we already have that. So that'll be a, e, e, right? Okay, f of 4, we have that as a base case. So whatever this thing is, okay, c plus a, e, e, d, right? Or I did something incorrectly. Sorry, let me think for a moment. So f of 0 would be, f of 1 would be e, that's correct, right? Okay, f of 2, 2 minus 1, f of 1, f of 1 is e, e, then plus e, that'll be 3 e's, right? No? Oh, okay, yeah. Okay, yeah, all right. Okay, f of 5. So, f of 5 computes f of n minus 1, so that'll be f of 4, and f of 4 is CE D, and that plus E would be this. Yes? Oh, yeah. Oh, yeah. Okay. So that's one. And this is a kind of question that probably shows up on the quiz. So just look at the function and figure out what will be the output. And you basically just start from whatever value I give to you, and then you work your way up the recursive ladder. Okay, let's see what other. This one is kind of similar. Oh, okay, old quiz question. Okay, so this one. Consider the following recursive function. What does it do? So just take a look at it for a minute. To what? Okay, yes, exactly. It's x to the power of n. So let's see why. Okay, so for example, if I take x equals 2 and n equals 3, what I will get will be, I will call this function mystery with 2 and 3, and this calls mystery multiplied by this 2, and then it decrements that one to the 2, and then x multiplied by mystery 2 and 1 over here, and then for the last one we just have, because this one becomes 0, we just say that's 1, right? So this is multiplying, so whatever we receive from this one, we multiply it by this, and in that case that would be x multiplied by 1, and in this case whatever I receive here should be multiplied there. That would be something like that. And then this is the return value of this one. So this is actually 2 to the power of x to the power of 3, or in this case this is 2 to the power of 3. And again, the way to figure out what a recursive function does, at least when you're starting to work on these practice questions, is that to go through it step by step and figure out what's happening. And here you can see that, okay, I'm getting this will be placed here, and then this whole thing will be placed here. Okay, what is the number? What does the number correspond to? What does the return correspond to? Okay. All right, this one is interesting. We have a couple more minutes. So consider this code. This is just a search code, searching for a value. Again, something similar to binary search, but not binary search exactly. So does the data need to be sorted for this function to work correctly? Justify your answer briefly. Okay. So take a look. Do I need to sort the data first, like binary search? Why no? Exactly. Yeah, right. It doesn't check whether the key is smaller or greater than a middle value or something. It basically goes through the entire data set, right? Because it has to compute whatever's on the left-hand side and also whatever's on the right-hand side. Consider the worst-case scenario. So in the worst-case scenario, the value doesn't exist in the list. We have to search through each element, search through the entire list. Okay, so left side, right side, we search through the entire thing. All right, now, what is the worst case time complexity of search in terms of n? So take a look at this data. O of n. Why O of n? We have to go through the entire data. And if we go through the entire data, this is the kind of thing that happens, right? Because we're splitting and then we're looking at the splits. So O of n, log n, 2 to the n, 2 to the n. Okay, but 2 to the n. That's only correct if we have n levels. Do we have n levels in this case? No. How many levels do we have? Log n. Stick log n in this equation. 2 to the power of log n, you bring 2 down, okay? Let me do this. So 2 to the power of n plus 1 minus 1, 2 to the power of log n plus 1 minus 1, and you can just disregard it because this is just a factor, right? And that will be n minus 1. Actually 2n minus 1. So it's O of n. You were right in the beginning, but for a different reason. Okay, so this is a very important point actually. If we have multiple recursive calls or something like that, it still depends on how many levels we have. Here we have log n steps, not n steps, that's the difference. And the log n kind of compensates for the fact that it's exponential. They just cancel each other out. Okay, this is a very important distinction. But let me tell you, it's actually not even O of n. And the reason is kind of because of in Python it's not O of n. Because in Python, whenever you do this, you're actually taking a slice of the array. And a slice, and taking slices is actually itself O of n, if you split it in half. Okay? So in this case, that would be, you multiply that by another n at each level. And so how many times do we do that O of n? We have O of n at each step, right? Yeah. So in that case, this becomes, in Python you cannot do that in constant time operation. So this is implementation dependent. I won't ask for something like this. And actually, originally this question, the solution was posted as O of n because that's what you need to think about. You don't need to worry about the implementation details. But just know that in Python, when we take slices, that slice also takes O of n operation time. Okay. All right, that's it for today's lecture. I'll see some of you tomorrow and the rest of you on Thursday. Thank you.